All right, finishing up chapter 5. We are in 511. We're going to find area under the curve, one more technique. It's our last one of the year. We've done it with trapezoids and rectangles. Now we are going to do it with parabolas. And this is called Simpson's rule. Simpson's rule finds the area under the curve using parabolas. There's two conditions that have to be met. The area must be divided into an even number of subintervals, chunks. An even number of subintervals an even number of chunks. And to make this happen, because we're going to be using a table, you have to have an odd number of x values. So just stop and think about why that is. If I want to find the area from here to here, and even if I want to go, I have to have an even number of chunks. Say I want to do it in 2 chunks. So I've got the area 1 here and the area 2 here, but take a look. It takes a beginning x value, this middle one, and this third one. So you need 3 x values to get an even number of chunks because you need that starting one and then your next 2 pieces. So you must have an even number of chunks, which takes an odd number of x values. That, and then your second thing is your subintervals have to be of the same width. Subintervals must be the same width. So your dx has to be the same on every chunk. All right. So just for notation's sake, so you know how all of this is going. So this is my equation f of x. Say this is the start of my area. I want to find this a value. And then I've got my chunks starting here, where the dx is the same all the way through here. So my starting x value, or I'm starting my area, they're going to call that x sub 0. Then the second x value that ends my first chunk is x sub 1. Obviously x sub 2, x sub 3, all the way down to your last x value. I'll just say x last, because there could be more in the middle there. But notice the first one is called x sub 0. All right, Simpson's rule. It's a lot like using Pascal's triangle, where you have the row with the multipliers. This has multipliers. So the integral from a to b, so a to b, of f of x dx using Simpson's rule. So We don't need to do any add 1 and times by reciprocal stuff. We're just going to follow this pattern. It's 1/3 times by that dx value. So how wide that partition is. And now here comes the multipliers. So it all depends on, you need a y value for every one of these x values. 1, 2, 3, and we'll go dot, 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 all the way down to our last. And I want to have 2, 3. Okay, the pattern starts out, and it's always the same pattern. 1, 4. I'm going to put another one in here. 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and it ends 2, 4, 1. So 1, 4, and then 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. It'll always end in that pattern. I got a dot, dot, dot in the middle here. So then those are your multipliers, just like Pascal's triangle has multipliers, and then all you do is you supply the y values. So because we've called this first x value x sub 0, we want the corresponding y value here. Y sub 0, then y sub 1, y sub 2, y sub 3, all the way down to the y sub last. So the second to the last, third to the last. So you're just multiplying by the y values and just crank that out in a calculator. So let's take one of these and go through and see how it works. So number 1, we are going to approximate the integral from 2 to 14 of f of x dx, where I don't know what the equation is, so I couldn't do it by hand, but I do have a table of points. And here's the table of points. X, f of x. And I happen to have them all evenly spaced. We're going 2, 4, 6, 8, 10, 12, 14. When x is 2, we've got 28, 43, 37, 33, 47, 68, 55. Okay, I would not, because I don't have the equation for this, there's no way for me to do this exactly by doing an antiderivative. So I am going to choose Simpson's rule. And to get the area from 2 to 14, I need to just follow this plug and chug formula. It's 1/3 times by my dx. How far apart are my x's? My change in x, and I can see that my dx is 2. So times 2. Then it's times this pattern. I've got 1, 2, 3, 4, 5, 6, 7. Remember, I needed an odd number of x's or I wouldn't be able to do it. 1, 2, 3, 4, 5, 6, 7. And now the pattern. 1, 4, 2, 4, 2, 4, 2, 4, 1. 2, 4, 2, 4, 1. And if you can't get it to end 2, 4, 1, you've done something wrong. And now we just put in the y values, and these are multipliers. So 28, 43, 37, 33, 47, 68, 55. So it's just a matter of plug and chug now with the calculator. Let's see how good I do here. 2 times I grabbed this thing, twice I used it wrong. So 1/3 times 2, parenthesis, 28 times plus, you got to add between there, plus 4 times 43, plus 2 times 37, plus 4 times 33, plus 2 times 47, plus 4 times 68 plus 55. I'm getting 551 and a third. And I don't have any labels for anything, so that is it. And I think the reason why this is here, this section's here, it's like, why again, why now? I believe the function integrate on the calculator uses Simpson's rule. So what you can do at this point, if you have the equation, won't work when you have a table, but all the ones on the test, you can use the function integrate to check to see if you've done this stuff right. Because I want to see all the work. I'm grading the work. You can get it approximately by using function integrate. And that is under your math. If you arrow down, you're going to see function integrate. And mine has the newer operating system that actually looks like an integral. If what you get is a parenthesis that shows up, then here's what you have to put in. If a parenthesis shows up and not this notation where you kind of know what to put in, you're going to put in your equation, then a comma, then you're going to put in the letter X, then a comma, you're going to put in the value for A, comma, and then the value for B. So, just to show you how this works. So if you had this on a test, I would make you show the work. You know, add 1 times by reciprocal, show me what you get when you plug in a 4 and a 1. But you could also just now check your answer on the calculator. You can put in a 1, enter. Oh, I didn't want that. Not that one. Up to a 4, then arrow over. Equation is X. Back this up. X squared dx. Now when you hit enter, you get 21. And we would have gotten that just like if I did x to the third times 1/3, 1/4. On a test, I'm going to want to see all of this. I want to see what you get when you plug in a 4. I want to see what you get when you plug in a 1, and then your final answer. So, we got 21 with the calculator. Let's see what we get. 4 cubed divided by 3 is 21 1/3. 21 1/3 minus 1/3 gives us our 21. So as a check, you can use function integrate. If you come up with an equation that we have not learned how to do, like this one, of 2 to the x dx, come chapter 6, we're going to be tackling these with logs, but for now, something like this, you don't know how to do, you would have to use function integrate or use a table in Simpson's rule. So if we type that one in, math, down to function integrate, we got 1, 2, equation is 2 raised to the x dx, 2.885. All right, there you go.